Hey, gang. Again, sorry I couldn't be in class today. I am assuming while I'm making this video, everything went well with my daughter's ultrasound. But for you guys, I want to talk about a different kind of family, and that is families of functions. We have been studying a long list of characteristics, which you can see kind of listed above here on the examples that condense target 1A and 1B together. Again, just a heads up, these are great practice problems. If any of these specific characteristics are still giving you trouble, there's more examples there in the notes and in the worksheet packet, putting everything in target 1A and B together. All right, done with that side commercial there. So all of these characteristics, again, we're treating them like DNA. And the reason we know that you are related to your family, well, biologically, is because we can check your DNA. And someone who has a biological relationship is going to have DNA that matches closer than any other human beings on the face of this planet, right? And so it's because of a specific set of chromosomes that identify you as a member of your family. And so we can do really the same things with our functions here, right? We have families of functions, and what you're going to see is an infinite number of different ways that a function can exist inside that family. But all of those infinite ways are still going to be related because they have some foundational DNA, some foundational characteristics that are non negotiables, which lock them into that family. We're actually going to be looking this year or from previous years in algebra at 9 unique families here. With you can see in 2 of the families, we'll have some multiple, more specific representations there. So linear functions, number 1 here, that's going back to algebra. You remember slope-intercept form, y equals mx plus b, point slope form, y minus y1 equals m times x minus x1, all that good stuff. Slope is a big one, right? Then we have kind of our 3 polynomial function families that we'll be focusing on: quadratics, cubics, and quartics. There are a lot more polynomials, but these will be the 3 that we'll mainly be zeroing in on, because essentially, if you can work with these 3, you can work with any of them. It's just a little more work to do the same things. Then we have our exponential family, which we'll actually be getting to next semester. But these are specific types of graphs that are very useful in life. If you've ever heard of exponential growth and exponential decay, that comes from our exponential family. Then we have our rational families. All right, rational families are where the asymptotes really get to shine. And we're going to be working with 2 specific types of rational families. The one that comes from the equation 1 over x and the one that comes from the equation 1 over x squared. That will also be split, some before first semester and some second semester, but we'll get into those more details of the equations then. And then our last 3 families fall into our trigonometric family. You might remember sine, cosine, and tangent from geometry, but now what we're going to do is, instead of limiting them to right triangles, we're actually going to be looking at them as a function over an infinite x and y axis, and you can see these are some of the graphs they look like. Now, what I've shown you here on the first page is what we call a parent function. A parent function is the simplest function in any family, which still preserves those unique characteristics which define the family. And so essentially, the way to think about it, guys, is that this is the starting point for every type of graph and function that fits in this family. So every line you have ever graphed started like this. This is the parent. And by changing the slope, by changing the intercepts, by changing different parts of the equation, you can create an infinite number of different lines. Same thing with quadratics. This is the quadratic parent function. It starts here with the vertex at 0, 0, and it opens up, and there's a specific pattern to how the points raise from the vertex vertically. As you change different aspects of the equations, you can change the vertex, you can change the direction, it can get skinnier, it can get wider, and we're going to review all of that. And this type of thinking applies to all of our different functions, families of functions here. What we're going to be doing today, though, is keeping it a little more basic, and we're just going to try and identify which family some children belong to. let's just pretend we're at a mall and a whole bunch of children functions are lost. And it's your job as Paul Blart Mall Cop. Yes, that's right, Paul Blart Mall Cop. If you have not watched Paul Blart Mall Cop, I don't know what you're doing with your life. There's two of them. Make that a priority this weekend. All right, your job is to reunite the kids with their parents. All right, now some of these are going to be a little more obvious, and some of them are going to be a little bit more unique. Now, on a test, we're not going to give you anything that's way out of bounds, but here's the deal. There are going to be specific characteristics that you're going to look for that at a minimum, you'll be able to reduce the number of possibilities, right? Here's the deal, guys. If the graph is straight the entire time, guess what? It's linear. If the graph curves, it's not linear, right? We can kind of do some of those basic things here. And we're going to be using the characteristics to kind of do that. All right, so here's what I want you to do. On these next 2 pages, I want you to pause the video, and I just want you to do your best job in terms of identifying which of these child functions, that's what 1 through 16 here, they're all children. They're all graphs that started off as a parent function and were changed in some way, but they still belong to that original family. So I want you to go through and take your best guess to match these 16 children functions to the 9 families that we have over here on the first 2 pages. All right, you ready? And pause. All right, welcome back. Well, tell me, how'd you do? You can see I tried to color coordinate the different characteristics here with their parents over here. And what I really need you to do, I'm not going to go through each of these individually right now. I want to keep the video a little bit shorter, right? But think about what questions you have. If you didn't match the children here with their parents, first of all, you're probably going to get fired as a mall cop. Secondly, you need to come back with questions on Monday. That is going to be so important, guys, because there are very specific reasons why each of these is matched with the parent. And more than just knowing these specific 16 examples, it's knowing the patterns, knowing, okay, why is 11 quartic and not quadratic? Because 11 looks a lot like number 1. Understanding why 15 has to be cubic and why it can't be quartic, like as it goes off the coordinate plane. Why does it just have to dip down to a relative minimum, a valley, and come back up, right? So please, guys, come back with your questions. We'll go over this. We won't go into a formative quiz on this stuff until I have answered all of your questions that you need answered on Monday. All right. Well, the last thing we're going to do with these notes is compare DNA. And again, going along with the idea that certain combinations of the characteristics of the DNA, of the chromosomes of these functions, define what family they're in. There are going to be some characteristics that cannot coexist in a family and some that can. And so what we're going to be doing, and there'll be one question on the test like these, where we're going to give you 2 characteristics. And what we really want you to do is think about the parents, the function families, the children that you just looked at, and think about, can I think of one of those families where these characteristics could coexist? And if the answer is yes, then draw a sketch. It doesn't have to be good. It doesn't have to be points, but it just needs to be a sketch. It can even be, honestly, one of the examples you already have on the previous page, right? We just want you to recognize these characteristics and what families are in. Now, if you don't think they can coexist, if there is something foundational in the definition of these characteristics that make them mutually exclusive, then we want you to explain what that is. And what that's going to do, guys, is it's really going to force you to understand these characteristics at a deeper level and not just at the shallow level where you can recognize them, but not really describe what they are or them in more detail. Let's just go through a couple of them here. First of all, a vertical asymptote of x equals 6 and a horizontal asymptote. So the question is, can we have a vertical asymptote and a horizontal asymptote at the same time, right? If I were to sketch those, that would, oops, that's the wrong way. How about I do the right one? So there's my vertical asymptote at x equals 6 and my horizontal asymptote at y equals -3. So here's the deal, guys. Just looking at those two things, can we come over here and either in the parents or in the children find an example of something that would have both a vertical and a horizontal asymptote at the same time? And I'm hoping as I'm talking, guys, you're looking at 10 and 3 and saying, yeah, the rational family, both the 1 over x squared and the 1 over x will have a horizontal and a vertical asymptote. So we would answer this question, yes, in the rational family, right? Rational family. And then just give me a quick sketch, right? It doesn't have to be something good, just something like that. Something that kind of looks like one of those, either of those two graphs, and that would get you full credit there. All right, let's look at number 3 here. Let's look at number 3, and I'll leave you to try 2 and 4 on your own, and then we'll come back and talk about them. Can we have a domain that goes from -infinity to infinity? So what this is saying right here, guys, is everything. This domain, a graph that goes from left to right with no stops, right? In other words, it is, what does that mean, no stops? It means it is continuous, right? We can put our continuous, that's probably spelled wrong, but I'm going to call it close enough for this purposes, because unfortunately, Myro will not spell check my handwriting. All right, and simultaneously, guys, can we have that characteristic with a vertical asymptote of x equals -7? Well, again, going back to our vertical asymptotes, what is that saying? This is saying we have to exclude every point with a domain, or x, right, value of -7. Well, let's think about this, guys. Can these things coexist? Can we simultaneously include every number from left to right with no stops, have it be continuous, and exclude -7 because it's an asymptote? And the answer is, hopefully you've come up with this answer is no. This is not possible, right? We can't even sketch a graph because it's not possible, right? And the reason it's not possible is we should know a vertical asymptote will cause I'll call it gap, right? Discontinuity, again, close enough. You can fix the spelling on your own notes if you would like to. A discon at the number x is equal to, right? So we know a vertical asymptote at -7 means at a minimum we have to skip over -7, which means there's no way the domain can include every number because it would have to exclude -7. All right? So why don't you go ahead and try 2 and 4 on your own, pause the video, and then come back and check and see how you did. All right, ready and pause. Welcome back. How'd you do on 2 and 4? You can see on number 2, we certainly can have a relative max at -3.7 and an absolute max of 11 because we can have multiple relative maxes, multiple mountaintops in the same function, just like a range of mountains can have lots of peaks, right? So we have our mountaintop at -3.7, but we will also have a mountaintop with a y-coordinate, a height of 11. Now, the x-coordinate doesn't really matter. I picked about 4 there, but you really could put it anywhere, and this would fit in the quartic family. You can see this graph right here that I drew looks like the inverse, like the flipped version of number 8, where we have 2 relative minimums, right, and a absolute minimum. So that would fit in the quartic family. The last one, number 4 here, of course, we can have an x-intercept at -4,0 and a 0, 7 because we can have multiple x-intercepts. So we have an x-intercept at -4,0, that would give us a real 0, and we have an x-intercept at -7,0, and that would give us our real 0 of -7. I realize it's +7 as I'm talking to you in the video, so let me erase that negative there. It says 7. I graphed it at 7, but for some reason I wrote -7. So guys, this is in the quadratic family. Now, to be fair, you could have easily sketched a graph that's a cubic or a quartic, or a number of different families would have worked, but the quadratic is probably the simplest, easiest one to draw that would prove that these characteristics can coexist. All right, so that brings us to the end of our time working with functions of families in these notes. To recap, what do you need to be able to do? You need to put on your badge and do your best Paul Blart Mall Cop impersonation. I'm probably going to add some images to the notes from Paul Blart Mall Cop now that I came up with that off the top of my head while I was making this video. All right, and you need to be able to take these graphs, guys, that you see here, and take these lost children and match them with their families based on the unique visual characteristics that we've talked about before that we see in the graphs. You also need to be able to look at two characteristics and decide, do they coexist in one of our families? And if so, sketch me a quick rough graph of that. Or if they can't coexist, if they are fundamentally opposed to each other, explain why they will never exist in a family together. All right. Well, guys, that's all I got. I hope you have a great weekend and you come back on Monday, guys. I really, really, really want to have lots of questions about this to go through because we dug into this and really thought hard about it over the weekend. All right. So I will see you in class on Monday with lots of questions. Have a good one.